Hi, this is an explanation for problem 96 in chapter 12. This problem reads, when you put on the brakes on your bicycle, friction heats the steel rims of your wheels. Could this heating be a problem? Suppose a 65 kilogram cyclist with a 15 kilogram bike is descending the Trail Ridge Road in Rocky Mountain National Park, going down a 7% grade, and thus losing 7 meters in height for every 100 meters of travel along the road. If the cyclist keeps a constant speed of 6 meters per second, and we assume that all of the lost energy ends up as thermal energy in the two steel rims, each with a mass of 0.8 kilograms, by how much does the temperature of each rim rise in 1 minute? Alright, so to conceptually, I guess to visualize this, I made this amazing little drawing with my little dude riding his bike down a hill. Now we've got a 7-degree incline, which is we'll symbolize this with theta. And then we also have our different forces. So we've got, what have we got here? We've got the normal force pointing up. We have friction force pointing back. We've got gravity pointing down, and we've got mass times gravity times sine theta pointing forward, and mass times gravity times cosine theta pointing back and away. So conceptually, this is kind of what's going on with the bike. Now to actually solve for this problem, we're going to use this equation right here, where Q, or the heat, is going to equal mass times gravity times V times T times sine theta. Now it's kind of a big equation, but we're given a lot of these in the problem. Really the only one that we have to solve for is sine theta, and we're pretty much given that one in the problem as well, because they said for every 7 meters you go, well, for every 100 meters you go down the trail, you go down 7 meters in height. So sine theta is simply equal to 7 divided by 100, or 0.07. So if we plug in our values, our mass is going to be the bike plus the biker, so 65 kilograms plus 15 kilograms is 80 kilograms, times our gravity constant 9.8, times v, which is our velocity, we were given that in the problem, 6 meters per second, times t, it's wanting in 1 minute, so 60 seconds, times sine theta, which I just explained is going to be 0.07, and that's going to come out to 1.978 times 10 to the 4th joules. Now, for our calorimetry equation, we're going to then divide that by the mass of both of our wheels times a constant of, or a specific heat of steel, which I just found online, 460.5. So because we've got two wheels that weigh 0.8 each, if we add those together, it's going to be 1.6 times 460.5. We do the algebra here, and we come out with 26.8 Kelvin.